I am here with Steven Perenov. It is my companion in this adventure. The show, as we always describe, is about using basically physics and the idea from physics to understand Bitcoin and explore its many properties, basically black hole you can fall in using a physics analogy and never come back, and we had a little bit of a hiatus there because I'm traveling in Europe. I'm still in Europe. In fact, I'm calling from my brother's apartment right now, and I had some internet connections and so on, but it should be okay. We are still figuring out the time. Probably next time we're going to do it a little bit earlier, so we can cover more regions in the world. But we will let you know. I will post it online, and I will let you know. We are going to keep this episode short, probably around 45 minutes, because I'm actually going to. I came back from Bulgaria. I will make some reports later about the things I learned from these conferences. But I was in Bulgaria in Sofia for a conference. It was very nice. I think actually it was my first opportunity to talk about the power law to a live public in a conference. I did it before in Seattle once, but this was at the conference, so it was very good. And it was a nice format because I could talk for about 45 minutes, and it was not enough to explain everything. But I'm going to Lugano today from
nice.
Plan B conference. Actually, I'm talking in a panel where we are presenting Bitcoin as a financial tool and long-term investment to bankers and financial institutions. So it's going to be pretty exciting. I was invited in that panel, and so they think that the power law is a good tool to introduce Bitcoin. That I'm happy about it. Okay. So I'll let Steve take over.
All right. We'll go to the top of the hour. It'll be a little shorter today because, Professor Giovanni needs to go pump up the price a little bit in Switzerland. So that'll be nice. Okay. Let me, I will just see how far we get. I've got actually too many slides today. This is Physics of Bitcoin 35. And I've titled this Towards a Grand Unified Theory. It's a little bit ambitious to use that label, but I'm trying to tie some things together. So that's why I settled on that. And ignore the times there. We're going to have different times next week. I think it'll be 11 a.m. Italian time probably it'll probably be more like 8 a.m. or something Italian time. We are now firmly in the zettahash era. We hit 1.3 zettahash in the past week. So it looks like we're going to stay in the zettahash domain or very close to it for some time. Here's the agenda around this concept. I'm going to introduce what gut in physics is, grand unified theory in physics context. And then I'll talk about why I use that label, because I wanted to tie together potential energy and kinetic energy and also dynamics. And this came about as I started thinking about when a previous show, Giovanni talked about least action principle. And one of the things that I've been concerned about probably for a couple of years is that the address count has been flattening. And so, how do we treat Metcalfe's law if the address count has been flattening in recent years? And we know the reason. It's because of a large shift towards institutional holdings. And so those addresses may hold a lot of Bitcoin, but they may represent a large number of people. And so we have to account for that in some way. And I'll talk about different ways you can approach that. And this is one way of approaching that, which is trying to have an analogy here with a dam, where you've got behind the dam, which is this wall of 21 million, its height is still growing. It's going to grow another 5%, but that's a wall of fixed height. We've got a fiat reservoir, and that reservoir is fed by the mountains, the snowbank. And the snowbank up in the mountains is the fiat liquidity. That's the macro world. And it comes down and fills a reservoir. And it turns out that can be our potential energy representation here. And then we can actually invoke Metcalfe's law for that. Then you have to release water from the dam. So you add channels. And what that does is has liquidity flow into Bitcoin. And then below the dam, you've got the level of the river below, and that's your price level. And you're getting price discovery. And so you've got institutional liquidity, you've got liquidity pools, you've got liquidity absorption, you've got channels opening up, you've got these dynamics going on. So I'll start with the gut model, potential and kinetic energy. In the simple case, you don't have any forcing function, but we know we've got an open system with forcing functions on the outside. So we've got a least action problem that has kinetic energy and potential energy, but it's got pumping terms as well. And I don't think we'll have time to look at the latest log periodic fits because we're not going to get through all of this. In physics, their grand unified theories do not unify all four of the fundamental forces. They unify the three forces that we have quantum descriptions for: electromagnetism, the weak nuclear force, and the strong nuclear force. And they each have their own carrier particles, photons or WZ or gluons in the case of the strong nuclear force. And then they have their own symmetries that are labeled here, U1, SU2, SU3, are the mathematical symmetries, what are called gauge groups for those. And they're, of course, separate forces in the world that we live in, but in the grand unified theory framework, which is unproven, but there's a lot of belief that it ought to happen, that there would be unification at very high energies, 10 to the 16th GeV, 10 quadrillion GeV, and 1 GeV is the energy equivalent of a proton, the rest mass energy. Now, the electromagnetic forces and the weak forces have already been unified. Weinberg, Glashow, and Salam received the Nobel Prize in 1979. I was fortunate enough to have Weinberg as my professor for general relativity. There are some problems, in developing these gut theories because we've never observed any supersymmetry. One of the great hopes of the Large Hadron Collider at CERN in Geneva is that they would observe supersymmetric particles. None have ever been observed, and no proton decays have ever been observed. There are different proposals that are made. There's one framework that explains the neutrino masses. There's a general belief that the way that the strengths of these, which is called gauge coupling, that we can observe, that they sort of point in the direction that there could be unification. But we have these other problems that we don't need to worry about today. But that's just kind of descriptive as to what it does. And the sort of questions that I'm thinking about are, why does Bitcoin bubble? Why are the bubbles quiescing? Why is volatility dropping? We know one reason is with the power law, you expect the returns to go down, and so you'd expect smaller bubbles as well. And another reason to believe that is we've got deeper and deeper capital pool as the market cap and the price have been rising, right? So the bubbles we can kind of think of as turbulence on the surface, and they become a smaller percentage of the total depth, of the capital pool. But what drives and allows the flows? At the macro level, it's global liquidity. Also, regulation matters. It tells you whether or not you're allowed to have exchanges, whether you're allowed to have ETFs, whether you're allowed to have a futures market, et cetera. All those things are open in the US and in the West. They just this week confirmed the first ETF in the UK. And then you have the micro level. So I'm going to talk about the micro liquidity in terms of liquidity absorption. And at the micro level, you have the channel availability, that regulation allows, but how many of these channels are there? How many exchanges are there? How many ETFs are there? How many Bitcoin treasury companies are there? So there's a capacity for those channels, and then there's a capacity to absorb liquidity, typically on the exchanges themselves. So what's the overall energy balance? You're shifting between potential and kinetic energy. I identify potential energy with the power law trend and kinetic energy with departures from that. Why is the address growth flattening and yet the power law holds up? So this is something I've worried about for a couple of years. And what happens with the shift from retail mostly to institutional mostly? So this is just quoting somebody else about, what's been going on in the market. But essentially, all of the purchase activity, all the net buying in 2025 has been by institutions. And mostly it's been by treasury companies, obviously strategy first and foremost, and the rest of it's been by ETFs. And as we know, some of the big whales have been selling at the margin. And Unchained said that the 2023-25 bull cycle has been primarily spot driven, shallow drawdowns, less downside volatility, make it easier for investors to allocate and hold on to their positions. Volatility has been in the 35 to 60% range, half as high as 2021 and a third compared to 2017. And then they say big money institutional capital has arrived. And that's certainly how I interpret things, is that it's institutional capital is changing the way it trades. Now, this is a chart that shows how the different institutional pools have grown. In the early days, it was miners, and then it was exchanges. And then, particularly in the past couple of years, it's been the ETFs. Public companies have been there for a few years, but they really have started ramping up a lot in the past couple of years. And private companies as well, and then governments too. And we just had another seizure by the US. That's over 100,000 Bitcoin. So governments are now over 600,000. Now you'll find if you add all these numbers up, it's too large. There's double counting going on, because in most of these categories, the private companies, public companies, governments, they're holding it on exchanges. So what that tells you is that there's been a shift from retail held on exchanges, because the exchanges look flat, right, to institutional holdings on exchanges as those have grown. So if we think back to the dam analogy, the channel expansion in the 2017 to 2020 kind of time frame, the primary growth was with exchanges. But in this market that started going up, right at the beginning of 2023, it bottomed in 2022. It's been ETFs, and particularly this year, it's been treasury companies, corporates. Okay, so the first thing you can look at, and this is an incorrect model, but it's the beginning of developing the model, is you can say potential energy plus kinetic energy. So we represent at first the total energy as potential energy V and kinetic energy K. And we're saying that this is part of the unified view, that potential energy drives long-term power law, and kinetic energy is seen in the bubbles and crashes and waves. Now, that could give you, there would be something like, let's see if this works. Could give you something like, sorry, it's in Japanese, but it's showing you, just a harmonic oscillator, kinetic energy and potential energy. Since it's in Japanese, I'll stop it. The last time I did it, it wasn't, but let's see what we're doing here. Then he goes on to show.
Stephen, we were not able to see the video at all, actually.
Yeah, it doesn't. It wasn't working because it was in. Okay, now I can't share the screen. Let's see. Hold on. Is there anything you can do on your end to help screen sharing? Because I think
I don't
that's screwed it up. It says
usually.
screen sharing is not allowed.
uh, do the normal share screening that you do?
Yeah, if I hit it, it says choose what to stream, but then it doesn't let me.
Okay, let me see just a second. Yeah, because I see a third. Okay, for a moment it was. I don't know what happened. Try again. Try again to sharing.
No. Let me just see about. Oh, well, part of the problem is.
You're not even be able to share your normal
Let's see where.
slides.
All right. Let me see about now. How about now? How's that?
Add to the scene. Okay,
Okay, there we go. How's that?
sounds good. Yep.
Oh, okay. Anyway, in that YouTube video, he went on to talk about the potential energy of, a ball raised to a height, or if you're up the side of a mountain. So I want to identify the potential energy with Metcalfe's law, which of course Giovanni discovered is the way the power law comes to Bitcoin.
So sorry, just to interrupt you.
Yes.
The main idea, I don't know if the video was showing that, this is something that it's natural for physicists to think. Maybe the public doesn't know, but in closed system, you can have a transfer of energy from what we call potential to kinetic, and the total sum is always conserved. So, for example, if you had a ball that is there is no friction, the air, you can exclude the air influence. The ball is perfectly elastic. As the ball falls, you see a change from potential energy to kinetic energy. When it reaches the ground, it's all kinetic. It bounces back, and you will see the opposite, where the ball loses kinetic energy and it gains again potential energy until it reaches basically the place where it started. And that will go on forever. If there is no transfer of energy to the ground, the ball will continue to bounce back and forth. I guess the video was about something like that.
Yeah,
right?
it was exactly that. Think about a ball on a string and you pull it up by hand. So it's got, gravitational potential energy because you raised its height, and you let it go. Then it accelerates, it picks up a velocity, and it swings back to the same height that you lifted it up to, but now on the other side. So it converts from potential to kinetic and back to potential, apart from any frictional forces.
Yeah.
So
If that happens, if a ball is perfectly elastic, of course, in reality, it's not. So some energy
yeah.
is lost to the ground. It is mostly heat. And then this is why the ball, in fact, that could be a model for why the bubble became smaller. I don't know if I kind of anticipating what you're saying, because
You are.
if you're a person, you see that the amplitude of the oscillation of the ball going up and down is
Yeah.
smaller and smaller and smaller, simply because it's losing
Yeah.
energy to the
Well,
environment.
it's a bit more complex than that. But
Yeah, of course.
okay, I want to take Metcalfe's law and say that the value, the market cap, or the price goes as some constant times time raised to the number of users, all raised to another index, which is Metcalfe's index. So the idea is that if the address growth goes as the cube of the age of Bitcoin, that gives you t cubed, and u would be 3 here in this little equation on the third line. And then gamma would be the Metcalfe index. So if it was 2, you get 3 times 2, and you get a power law of 6. Well, what we find in networks that gamma, the Metcalfe's index, is typically around 1.5 to 2. And so the user wallets are going as t to the u, and the network value is going as roughly user squared. So in that sort of simplest case, u is 3, gamma is 2. Overall, you get the value of the network, which is this potential energy, is stored. It's storing value, right? So you store value in this thing, and then you get price discovery when it gets released. And that goes as, say, t to the 6. So this is the long-term potential. It grows as the reservoir is filled from fiat streams behind. Obviously, there's a conversion mechanism. People are buying. So it's coming down from the mountain, in little rivers, and the snow is melting, and it gets converted into Bitcoin in this reservoir or in the network, and has this potential energy. And the price discovery happens after it falls out of the dam. So the dam and the reservoir in this analogy are Metcalfe's law network with stored potential energy. In the case of a dam, it's gravitational energy, and it just goes as the height. The height of the dam tells you how much you can store, and obviously the volume of water behind the dam. Okay, well, why have I been worrying about this? And we've only got 20 minutes left, so I'll really just have time to sort of set up the problem.
And we can do more episodes. We can
Yeah,
chapter 1, and we can cover it later.
yeah. And there's an article on this. If people go to my Substack page, they can see the first of what's going to be 2 articles on this. But what has kept us on a price going is age to the 5.7 or 5.8 power law if the address growth is flattening. And here I'm plotting the address growth over time, and the top is a log-log plot, and the bottom is a log linear plot. So log of address count in both cases, log of age in the top graph. And, they're roughly straight lines, but not exactly. But the slopes are changing. And the slope starts out as 2.3, and then it goes to 3.2 in the next 4-year epoch, and then it goes to 2.35 in the following one. But in the last one, and I include the present epoch 5 that we're partway into. So I'm going really from the 2020 halving until now, 5.5 years. It's grown as 1.58 power of age, of Bitcoin's age. So if you want to preserve this 5.8 power law, and if you're growing your address count at 1.58, you have to have a higher gamma, right? So gamma would have to, in fact, be about 3.7, which is not something typically seen with Metcalfe's law for networks. Or, you're not counting your addresses right.
Well,
and this is
you go ahead, but I have a comment on that.
Sure. Let me just finish this. And
Yeah,
then
exactly.
Comment. So this is non-zero addresses. The addresses have to be increased substantially because you have to allow for this institutional custodianship. And we've always had this. We've always had exchange accounts where they've, put multiple users Bitcoin into single addresses on exchanges. And now, and then certainly with the ETFs, you have the same phenomena where they're representing potentially many users, right, with one address. I'm not saying they put all of it into one address. They may put it into 100 or even 1,000, but it doesn't represent the number of users they have, which could be hundreds of thousands, right, for a major ETF. And then the equity shares, how many retail owners are there of Strategy? Millions, right? But I doubt they have millions of addresses. So we're miscounting, right? And we're particularly miscounting in the last few years. So what I want to do is try to model this in a different way by thinking about how the institutions are drivers of capital flow. Now, I'll pass it to you for your comment.
Yeah, my comment is, and I don't know what you're going to explain. I didn't have a chance to read your article, but so that is a possible interpretation. So you could say, okay, these institutional addresses, what is the real representation in terms of single users? And I don't know how you do that. The other is to think about this institution as whales. And in the case of a network, because we already show that, right? You did show that, I did show that. I did graphs where I took different cutoffs of a wallet, and I saw what was the relationship between the growth and the response, right? What is when you look at price versus addresses, basically the Metcalfe flow, right? Or a generalized Metcalfe flow. That is called, there is a technical term for that in network theory. It's called densification, the densification of a network. Now, when you have a network that has a very, very strong nodes that are stronger than others, then you will expect the densification to have a higher slope. So, in fact, if you, I don't know if you did it, but if you, and it's logic, right? If we keep this slope in the price versus the time, pretty consistent because it does not change much, right? That means that the response of price versus addresses has to change to compensate for that. And if you actually do the graph, is exactly that. If you can do the same thing that you just did, kind of piecewise, and see that the slope is changing both for the addresses versus time, but also price versus addresses to keep this, to keep the overall power law in time the same. It has to be.
Right, but I'm trying to get at the why. So
Yeah.
I think the why is institutional, and then the question is, okay, if the why is institutional, how do you model this? And one way would be to count the addresses properly, but we don't know how to do that. We don't know how many retail shareholders Michael Saylor has.
Yes.
And we don't know the distribution of their balances.
Correct.
Right. So we can only make guesses there.
Yeah.
So what I want to do is kind of capture all that into a couple of simple terms.
But I'm saying from a network point of view, you can consider this big institution like very strongly connected nodes. And then it's actually natural to see an exponent for price versus addresses that is higher. So a higher gamma is unusual, but it's actually part of a network theory.
The fat nodes cause it to have power law behavior.
Exactly.
And this just shows this to some degree. I just took the address growth for balances above 1,000 because I said, well, if you don't have $1,000, it doesn't matter that much, right? And so here, what you see is today, it's still a 3.2 power law with the last 5 years, and a 4.9 power law prior. Now, it's a little bit artificial because as the price grows, a lot of addresses cross the boundary of that cutoff, right? So $1,000 cutoff was very difficult to get over that barrier in 2011, right?
Yeah.
And so it had very rapid growth as the price was growing rapidly.
You can use Bitcoin as a cutoff.
That's another way, and we've done that in the past. Yeah. Anyway, this is just kind of an aside. Most people care about how much it's worth to them, even in fiat, because they have to live off of it. Okay, so here's the dam analogy. So if the reservoir is the market cap that's constantly revalued by price discovery, and liquidity comes from the melting snow and streams from the TradFi mountains, the spillways out of the dam are the channels for purchasing for flow to buyers. So that's principally exchanges, ETFs, treasury companies. So you can add new channels, you can have new ETFs, just like this one opened in the UK, or they can be wider, they can service more clients. And the river downstream is the price level, and that rises with more channel capacity. But it also falls. It falls when people sell. That's called, on the micro level, this is not macro liquidity, this is micro liquidity absorption. And so that's retail sales, especially whales, it's trading pools on exchanges, it's the leverage, the futures and the options and the loan facilities. And as the amount of leverage varies, the amount of liquidity absorption can vary pretty rapidly. Okay, so we don't have a harmonic oscillator, because we've got forcing functions here. On the positive side, the channels; on the negative side, the liquidity absorption. And we actually modeled both of those as power laws.
Mm-hmm.
And the reason I did that is because I've noticed that the institutional holdings for the last few years, or really over the lifetime, have grown as the fourth power law of time. And this index here is the flow rate. So it's actually the first derivative of their holdings. So it's something like the third power.
I like this idea. It's a very nice idea.
And then the liquidity absorption has to soak up the capital flows. So these are the dynamic terms. You're pumping, you're more subject to turbulence and volatility as channels are added or lost, or, regulation changes. There's a whole new set of channels that becomes available, impact from macro regulation. But then there's market liquidity structure, in the exchanges and other market influences. The money supply would be in the background for the macro global liquidity. This is just the growth of institutional holdings. I've shown this before, and it's growing as something like the fourth or 4.5 power with a very good R squared. And it includes corporations and ETFs and the trusts before we had the ETFs. And governments, insurance, hedge funds, DeFi. And you can see the power law fit there is pretty good, R squared 0.95. You see a kind of flat zone around 2021, 2022 when we had the breakdown. But then it recovered very nicely with the ETFs. So the flow rate is the time derivative. So it's just T to the 3 or T to the 3.5 in principle, over a long period of time. So we're basically, instead of breaking down all these address contributions, we have an overall contribution as a power law for channel capacity with index C, T to the C, offset by liquidity absorption. So that's a 1 over T to the L, where L is a power law index for the liquidity absorption. I make this an observable. So I know what the others are. I measure the U, and I measure the gamma, and I measure the C, and then the liquidity has to respond in order to kind of keep things to restore the balance. And so what I do is I say the balance is defined by this equation K, which is the power law index for the price of Bitcoin, is equal to the Metcalfe potential, which is U, the growth in users, times gamma, which is, something like 2 or close to 2. So U is the user wallet growth index. Gamma is the Metcalfe's law index. And then we have a positive C and a minus L. So the institutional holdings flow exponent, that's growing with time normally. And then L, the liquidity absorption, if it's positive, would offset. If it's negative, would actually contribute. So price still goes as T to the K, but now we've got 4 index components. We've added a pump, and that pump is C minus L. We'll see something like 3 on average. Mm-hmm. And the kinetic energy, we say, well, that goes as the velocity squared, because that's what kinetic energy does in Newtonian dynamics. And so those are the short to intermediate bubbles and waves. So this is what ChatGPT thought about the dam analogy. It says, yes, it has the right ambition to be called a kind of grand unified theory of Bitcoin price dynamics. Mm-hmm. This just repeats basically what's on the prior slide. Balance of the network effects, the potential energy, the capital rails, and the liquidity absorption. It provides some conceptual decomposition of Bitcoin's power law exponent. And it gave a couple of simple cases, if you need to hit K equals 5.8, and, if U were 3 and gamma were 1.5, and C were 3, you'd have no liquidity absorption. That would be zero.
Yeah.
But if gamma were different and U were different, you know, and C was still 3, then you would need some liquidity absorption.
It's pretty nice. It gives more depth. Yeah.
Yeah, this is a heat map where you assume K of 5.8 and C of 3. And then for different values of the Metcalfe index and the user wallet growth, then the colored curved lines like the yellow line, L equals 3 and L equals 2.5, are the implied liquidity absorption you need to keep everything in balance over the long term.
Yeah, it's nice.
Okay, so there's also a virus analogy here.
Yeah.
Which I'm sure you've made multiple times. Replicators will settle into fitness exponents. So as the network kind of develops and grows and kickstarts, and this is seen in viruses, it'll settle into some fitness exponent. There'll be an emergent exponent of a self-organized critical state.
Yeah,
and that's what we've seen happen with Bitcoin. So we're saying that the adoption and the rails and the liquidity adjust. Adoption can slow or shift toward custodians. Liquidity providers follow, you know, they try to make markets. Price overshooting is going to attract more liquidity provision.
Mm-hmm.
And I did write an article on Substack with asking if Bitcoin were alive. And I said, well, no, but it's like a virus.
Yeah, that is the closest non-alive things to something that is alive.
Yeah, it's not fully alive, but it has to have a host, and we're the host.
Yeah, it has
we're
life
happy
properties, but it's not fully alive. Yeah, it's on the border.
Yeah, we're happy to be hosts.
Yeah. Another analogy is fire, like how fire spreads, for example.
Yes.
Forest fires.
Okay, so we've got a constraint, which was that equation for K with the 4 terms. Now we need a Lagrangian and a least action principle. So we have a kinetic term, which goes as a velocity squared. And that's now the residual. So what I've done is I've taken the power law, and then I've taken the price residual, and then I take the time derivative of those, and that's my velocity.
Mm-hmm.
I square that. So that's the kinetic term. And then the potential term is U times gamma, you know, so it's the power law itself, basically, with the Metcalfe realization. And then the forcing term, F, is C minus L. It's a pump term of, you know, the increased capital flow and then the liquidity absorption.
Yeah.
So if you look down in this white frame, you'll see the actual Lagrangian equation, which goes half M delta dot squared. So that's your velocity kinetic energy term. And then there's a term which is the rails flow term, and that has a, you know, exponent alpha, or sorry, a constant alpha in front of it.
Mm-hmm.
And then there's a restoring spring term, which is a potential energy term, and that's got a strength kappa. So the first term is the inertia. The second term is a pump. And then the last has a quadratic potential, which is a restoring pullback to the core. And so K is the stiffness of the spring.
Yeah, because when I was fooling with this idea from least actions, I was looking for a Lagrangian, and, you know, for example, ChatGPT was proposing few, but none of were motivated foundationally like you're doing. So this is very cool.
So here's our least action applied to the Lagrangian, and then we get the Euler-Lagrange equation of motion, which is in the upper left. So then it becomes the acceleration, delta double dot, and that's the acceleration on the price residual.
Mm-hmm. And
M is the inertial term. And then kappa is the strength of the restoring force, which depends on, you know, it's our Metcalfe, it's our power law potential with U and gamma.
Yeah.
Times delta, which is the size of the residual itself, and these are all log residuals, right?
Mm-hmm.
And then there's the forcing term, which is the time variation of C minus L. times this alpha. So that's the setup. I think I'll stop here because we're at the top of the hour.
Yeah.
And then we can cover more later. But you can solve this and you can model it. And I've shown, I will show you, next time how it does.
Well, you can show a preview because I'm too curious.
Okay. Well, if you take it over the full history, and when I say the full history, I mean recent years. So this is the past 5 years.
Yeah.
It gives you a spring strength with a good probability. You first of all, you set the mass term to 1 without loss of generality. Okay. Sure. So the spring term is 4.6. The error on that is 1.6, but the R squared is very modest. But this is over the whole history. So you can see the wiggles kind of fit. And that's the acceleration actually that's being plotted. The observed acceleration in blue and the fit. It doesn't explain it very well, but acceleration is also a very noisy series. So it would be very hard to fit. So it says, yeah, there's something to it, but it's not that great. But there is a strong restoring force. There's a big kappa. Right. And the pump term is not significant here. Okay, so I said, well, it's going to be clearest in the bubbles where we're stretching the spring more, right? So I look at the 2021 bubble, and the definition of the bubble is greater than 0.2 in the residual, that's the log change in price, and then greater than 6 weeks duration, and that gives the bubble shown in the small chart up at the top that extends from age, a little before 12 to a little over 13. That's the 2021 bubble. It's double humped. And we're fitting the acceleration in this big plot, and it does fairly well.
Yeah, I can see. Yeah.
The fitted line is the orange. The blue are the observed accelerations. And I broke it down into the spring and pump. And what we find is the pump contribution, actually changes sign towards the end, which is kind of interesting. So it takes a while to grow and fall. And, I think I can kind of explain that later. But both terms are significant. The spring term is significant at the 6.6 sigma level.
Oh, nice.
The pump term at the 5 sigma level.
Wow.
Which is good enough for, discovering a new particle.
Yes.
And the R squared is 0.48, and the probability this happened by random is very low. 10 to the minus 7. So there's something to it.
It's a beautiful model. Yeah. And, and this is the first iteration, so it can be improved.
Right.
Very good. Let's stop here.
Let's stop here, yeah.
But I can see where this is going. It's very cool. I love it. Because this is really bringing physics idea, and we are all meaningful, right? Because we're talking about cash injections, we are talking adoption, we're talking about cash flow in both directions, so it's very good. It's very nice to see this. Okay, and I want to do something similar, but from the network angle, and see how, like talking about strength of the different connections, etc. I don't know if I will go anywhere with that. I started to read more and more papers on the topic. The price is a good indication of the links, but it's not a direct one, right? Because it's almost like a tautology, because we say, oh, the value of a network is in the price, but then you don't measure it directly, so you're assuming that is the case when you actually have to prove it in a sense.
Right.
So I'm going to see if I can download the data directly from the chain and see, I don't know, if I can measure the connection between the addresses, maybe through transactions or something, and see where that is going. But then we could compare nodes, because I think the macro description should be consistent with the macro, right? So the two
Right.
And I think of a network approach is more like, from bottom up, while the physics one is from top down, and the two should give similar results. But yeah, it's very interesting. I really love this approach. Very, very good result.
Thank you.
I
Thank
will,
you.
I will try to validate it myself when I have a
Yeah.
chance and reconstructive steps.
Yeah. The hard part is measuring C, but I found monthly measures, so C at monthly intervals.
Yeah, because this is the next step as a physicist, right? You start from observation and empirical modeling to actually
Mhm.
models, right? Real models, no empirical models, but theoretical models where you can reconstruct the behavior from first principles. So that is what we call model. We almost never use the word model to describe the fit, of the data. For us, model is actually what we call a toy model, right? We make the simplest possible model, even if sometimes seems very simplified, but it capture the dynamics of what we're trying to describe, and that is exactly what you're doing. So very, very, very good. All right, I think I need to start to get ready for my trip. We will try to see each other again next Wednesday. Um, we will announce a new time, probably will be earlier than this, so more US people can join us because it's late over there. But I will post some announcement on X. Probably you do the same, Stephen.
Yes.
All right, thank you, guys. I don't see many questions, so and we will not have time. Maybe next time we will do that. All right,
Thanks,
bye, everyone.
everyone.